Awesome. Thank you so much, Juan Miguel. That was that was a very nice introduction, and I should probably just add that that coolest math nerd award was given to me in high school. So yeah, I don't know. I don't think that holds any weight, but thanks for mentioning it, and yeah, thank you for inviting me and having me here. I'm very happy to be here, and I'm a very big fan of QHack, so it's always an honor to speak. So yeah, in the interest of time, I want to just tell you a little bit about background of the talk and some of the research that we're doing. And I've called it model capacity in machine learning, but really it is going to be about a specific way to measure capacity for machine learning models. And if you're interested, I've put the archive link of the paper that I'll be referring to mostly throughout the talk. And this was in collaboration with some colleagues at IBM, David and Stefan, and Alessio, you might recognize from ETH. He's one of the most recent Fields medalists. So this was really quite an honor for me to work with these people. They're very talented. And so last year, if you attended QHack, you might remember that I spoke to you about a similar sort of idea, a notion of how do we measure expressibility, specifically in quantum machine learning. And a lot of what I spoke about, so I just took the screenshot from the talk, it's still up on YouTube if you're interested, is this idea of what I call the effective dimension. And we use this measure of capacity, which I'll explain a little bit better just now, called the effective dimension to understand how do quantum and classical models look in terms of this measure. And so this was like what came out in this paper, the power of quantum neural networks, where we found a distinct difference in this measure between quantum and classical models for restricted classes. And while this was really interesting, and we were very excited about it because we we finally found something that looked different and interesting about quantum models that was promising. We actually, I think, looking back in hindsight, missed a very, very important thing about capacity in general. And so I feel very proud of this work, but not actually for what it's known for, not for this distinction, but for this measure that we proposed in this effective dimension idea. But we didn't do it properly. In my opinion, we didn't do it justice. So the paper that I referenced on this title slide, you can think of it as a continuation of this work, and it's what I want to tell you about today. And in short, what we do is we kind of refine this measure of capacity, and we call it a local version of the effective dimension, so a local effective dimension. And the difference between the effective dimension that I introduced last year and what we use to analyze quantum and classical models is very, very subtle to when compared to this local effective dimension. Subtle, but a very crucial difference and distinction exists. So what I want to hopefully deliver today is really just three things. One is that what is the local effective dimension? Well, intuitively, you can think about it as a way to measure redundancy in your model. So how useful are my parameters in my model? Are a lot of them redundant? Are a lot of them important? That's basically how you can think of the local effective dimension, as telling you how much redundancy there is. The second thing, and this is a bit of a more difficult thing to convince you of, is that the local effective dimension, in my opinion, is a good measure of model capacity. And I'll tell you what capacity means just now as well. And if it is a good measure of capacity, which you've probably heard about in previous talks as well, this idea of model capacity in machine learning, then it should give us good insight into generalization performance of a model. And I know this is something that has been spoken about a lot. So we won't go through the definitions in much detail, but these are the three things that I want to deliver to you. And overall, you can just kind of well, I hope to convince you of today. If you take one thing away from this talk, it's just that this idea of the local effective dimension is useful in some sense in a machine learning setting. And then what it means for quantum machine learning is still open. So we can discuss that after. So just very quickly, what is this relationship now between generalization and capacity? And in my opinion, and it might be a biased opinion, generalization is one of the most important things to study, understand, and question in machine learning theory, right? So what is this relationship that exists? And we all know about generalization and generalization error. We have some machine learning tasks. In a supervised setting, we train them on stuff. So let's say classifying pictures of flowers. And the whole idea is once we've trained a model, how well does it do on out of sample data? Can it generalize well to new tasks? And the error that it makes is this generalization error. And if we have a model that is parameterized, right? So it takes in some data X and depends on some parameters theta. What can we say about this model? What statements can we make about it on unseen data? And typically, what we do is we try to address this question theoretically, where we know that if we pick a model to model some relationship that exists in nature, then there will be some true error associated with our model, right? Because there often isn't a very clear way to pick the right thing, and whatever we pick will have some inherent true error. And we can approximate this true error with empirical data. Right? So we have data, we have training data, we can kind of approximate, and n here is like the number of data samples that we have available to us. So we try to approximate this error empirically. Now, the difference between our true error and our empirical error, approximated error, is what's called typically the generalization gap, or some people even refer to it as the generalization error itself. And when we try to bound this, well, we say, okay, for a particular parameterization, for a particular theta that exists in our parameter space, we take the supremum of this difference, and the probability that this difference is greater than or equal to some value here. We try to understand how can we model this, and how can we in particular bound this quantity so that we can like really understand it and understand how good our model is and our choice for a machine learning task. And there's been beautiful progress on understanding this notion of generalization error for models, so how well your model does in unseen data, by relating it to capacity, right? So the capacity of your model. And in particular, this capacity term usually depends on things like the number of data you have, and also like the size of your parameter space, or your model space, or your model class. Okay, so how do we measure capacity then, right? And firstly, what does capacity even mean? So in classical machine learning, well, it's used interchangeably with a lot of terms, and this actually confused me when I went down the rabbit hole of trying to understand the effective dimension. What does capacity even mean? Because these terms are all thrown out: statistical complexity, expressivity, the power of a model. But in my head, I kind of just think of all these things as just one thing, where you're simply trying to understand how many functions does my model approximate, right? So what is the richness of my model in terms of the functions that it can understand, it can model and express. Okay, so now naively, one might think, I want a model with infinite expressibility, right? Like a higher capacity should be better, because then I can throw any data at it and we'll be able to model the true relationship. In this very silly, simple cartoon, we can immediately see why this is not the case, right? So let's say we've got this just two-dimensional data. So each dot here is a data point. And we're trying to understand this relationship between X and Y. Now, if we pick a model that has very low expressibility, so very low capacity, let's say something simple like a linear model, and then we try to use this model to understand new data and make new predictions. Now, if we've got a new data point, let's say this blue dot here, well, then our model's not going to do very well, right? It's obviously going to make a lot of mistakes. And we say this model that's very simple, it doesn't look at the training data enough to learn a true relationship. And so we say this model has a high bias. Now, on the other end of that, imagine we've got a model that's like super intricate and tries to fit every single data point here. And now when we have a new data point to classify, well, this model that's super intricate will also make mistakes, right? So if this is our new data point, we read off this curve, we'll see that the error, that the approximation will be quite different, right? The predicted Y value from this curve will be around here, whereas the true Y value is something around here. So this model is something that we say it has high variance. So the variance that it will have on predictions on new data that comes in is very high, and this is not desirable as well, right? So we want something that kind of trades off these two things, something that's simple but not too simple, and complicated enough to learn a relationship that is true in general, right? So there's this bias variance trade-off, which a lot of you will already be very familiar with. So picking a right model really is very closely related to this notion of picking a model with an optimal capacity, right? So you want to choose something that's expressive enough that your model doesn't overfit and doesn't underfit either. And in doing that, you minimize this idea of this generalization error. So, and the bias variance trade-off is very easily, I think, depicted in this graph, where as we increase the capacity of our model on this x-axis, we see that the variance starts to increase. And then when we have a model that's very low capacity, we have a high bias. Okay, so why am I telling you this? Well, how do we measure this thing on the x-axis in the first place, right? How do we understand what to put here? What is capacity? Is it number of parameters in my model? Is it, I don't know, VC dimension, or what's good here? And well, why? If we can understand how to measure capacity, well, then we know that we can understand generalization behavior with that, right? Or we hope to, because we know that we can usually study, or there is a relationship that should exist between generalization and a good measure of capacity. So in classical machine learning theory, there are tons of notions of capacity, and a lot of them are very good, but often fall short in certain characteristics and certain properties. So what I wanted to tell you is just an idea, a rough framework for properties of what makes capacity measure good. This is in no way an exhaustive kind of list, but I think it picks out and highlights what I believe is some of the most important attributes for a good capacity measure. So firstly, of course, if you're going to propose a capacity measure for a model, let's say neural network or whatever, the first thing we need to show or need to be certain of is that it actually does bound generalization error, that we can have a proof for this, so we can use it to study generalization and probe generalization error behavior. So this is the first thing that is pretty important when it comes to proposing a new measure of capacity, whatever this is. The next thing is the notion of capacity. The measure of capacity needs to be able to capture your under and overfitting. So say now the screen curve is the generalization error. Typically, we want a capacity measure that kind of correlates with this behavior in both regimes, in this underfitting and overfitting behavior as we train our model. And so, so we want a capacity measure that kind of moves in unison, like in harmony with this idea. And this is also actually not trivial at all, because there's whole arguments about deep neural networks and why they don't overfit, but there are settings where we can force them to overfit. And so testing your capacity measure in all these different experimental setups is actually quite important to see if it really does correlate well with generalization error. Then that's typically a good sign. The next thing you want with your capacity measure, and remember now, capacity is just trying to understand the expressivity, the power, the statistical complexity of your model. You want it to be scale invariant. Now, what does that mean? Now, imagine you give me a neural network, and I want to be able to tell you, okay, what is the capacity of this neural network? What is the expressivity? But if you give me the same neural network with weights that are just multiplied by some scalar value, that's going to be the same, essentially the same model, right? Which is weights that are multiplied by some inconsequential transformation. Then wouldn't it make sense that those models, whether you multiply your weights by a constant value or not, they should be able to express the same sort of functions, right? And a lot of capacity measures actually are not scale invariant. They are sensitive to transformations that are inconsequential to a model. So if you multiply a neural network by some scalar value, multiply the weights, some capacity measures are influenced by this transformation, even though this transformation has no influence on the type of functions that the model can express. So this is an important property for a capacity measure to have. The next thing is that your capacity measure should be able to incorporate the idea or the notion of having finite data, because in reality, that's all we typically have, right, is finite data. And so while a lot of capacity measures are beautiful in theory, they have a lot of desirable properties, like the VC dimension is one of them, but they make the assumption that one has access to infinite data, which of course in practice is not possible usually. All right, and now one that I think is very interesting is a capacity, and I think this is a little bit of a newer notion and a newer finding, thanks to deep neural networks, is that the capacity measure needs to incorporate the learning algorithm that we use. So things like gradient descent and stuff that we know very well, that works very well as well. Our notion of capacity somehow needs to incorporate the fact that we use learning algorithms in it. Now, how and why? Well, let's take, for example, the VC dimension, which does not, right? So it does not incorporate the notion of a learning algorithm. What does the VC dimension try to explore or understand? It tries to understand the size of your full model space. So you give me a model class or a class of model families, or however you want to say. Let's say a neural network with a particular architecture. Then the VC dimension tries to understand the space, the full space of functions that this model class can represent, can learn. And while that's good, that's interesting, and one would think that that makes sense to understand and use as a capacity measure. What we do when we impose all our constraints, like such as training and so on, is we actually restrict the space that we are interested in and have access to. So in reality, what I mean is that we impose restrictions, we impose optimization algorithms like stochastic gradient descent, Adam, and so on. We specify a certain data with an inherent distribution, and we often only have finite data. And so with these imposed constraints, like a learning algorithm, what we're doing is we don't actually have access to this full model space. We have access to a restricted model space. So why should it make sense to study the capacity of the full model space when in reality, what we have access to and what we would ever have access to is actually a much smaller subspace of this thing. So a lot of newer capacity measures keep this in mind. They realize that gradient descent only allows us to move a certain amount in parameter space, which means that we only have access to a certain level of expressivity in this full model space. So this is this was quite a realization for me, because I didn't understand this. It took me a while to understand this, and I think people are still trying to actually understand what does this mean, and what does this restricted model space look like. Okay, so now finally this brings me to the thing that I want to tell you about, right? The effective dimension, the local effective dimension. And I just listed here the properties that I took you through, and some popular capacity measures. And lastly, this idea of a local effective dimension, which I'm going to show you now, ticks all these boxes. And by the way, if you're interested in this stuff, I can point you to some resources here about capacity measures. And in particular, there's a really nice kind of literature review about different types of capacity measures that exist, and their benefits, their drawbacks, and so on. So this last paper here, Fantastic Generalization Measures and Where to Find Them, is quite a good place to start. All right, so like I said, originally we started with this idea of what I called the effective dimension. And the effective dimension, if you remember my story, is like trying to understand what is the size of your model, of like the true size of your model, which is typically existing in a very high dimensional space. So the analogy of clouds in the sky is the one I always use, where like clouds exist in a three-dimensional space, right? But the fractal dimension, the true space that they actually occupy, their effective dimension, is 1.37, right? Because they don't occupy the full three-dimensional space. So similarly, like if you have a model, a machine learning model that has lots and lots of parameters, right? It's like this really, really high dimensional, over parameterized model. What is actually useful in that? What is the true size of your model? What is the true substance there? And in some sense, the effective dimension in trying to understand the true size of something can also be thought of as a measure of redundancy, right? So like if you're trying to understand what size of your model is actually important, is actually active, then it's also telling us how much of that model is inactive. And I'll tell you how it does that. So if you remember, we use this quantity to explore different quantum circuits and classical circuits, and we found a difference which appeared to be exciting. And what we did was we used the effective dimension to measure the expressibility of different circuits and different classical models. Now, the effective dimension is quite, I think, simple to understand intuitively when we think about these different spaces that we can have when we have some model family F, some data X, and then some parameterization for our model, right? So there are two spaces at play. One is the space at which your parameters exist in, right? This parameter space. And then the other is is the space of which your models exist, right? So remember now, the full model space is like the full space that your model family can, the full set of functions that your model family can express. And in some sense, you can think of like each point here in model space as a particular parameterization for a model. So you can think of it as like a distribution. Let's say a distribution like an output of a neural network, for example. Each point in model space is a neural network output distribution for a particular parameterization. So for a particular theta. And then all the thetas, they can think of them as parameter sets that exist in this space here. So how do these two spaces relate and how do they talk to each other? There's various ways, but I think a very interesting one is this notion of the Fisher information. So the Fisher information allows us to understand the relationship between the sensitivity of my parameters to my model space. So if we just think about one parameter set, theta in this space here, then if we take the determinant, the square root of the determinant of the Fisher information with respect to those parameters, we get a notion of volume, of size of a model. So so that's quite interesting, quite nice. The Fisher information gives us a notion of distance, of size, of volume in model space, in the space that we're actually trying to study and understand. And so now the formula for the effective dimension, which is quite a long one, is something that depends very heavily on this quantity of the Fisher information. So if we look at this formula, what this is saying is it's saying, okay, the effective dimension, which we just call D, depends on some parameters, some hyperparameters, and n is the number of data we have available to us. Gamma we can essentially ignore for now. I can think of it as a fixed hyperparameter that equals 1. And so the effective dimension D of some model with a how do I say, parameter space theta, capital theta, is defined like so, where I think the most important thing to look at is this highlighted part of the equation, where we've got an integral here, and this integral is taking an average over the full parameter space, the full capital theta. There's a square root of a determinant, and in there is a Fisher information, right? So we remember I said the square root of the determinant of the Fisher for a particular parameter set gives us a notion of volume, of size. And so now what we're doing is we're kind of like averaging over all models the square root of the determinant of the Fisher. So we're averaging over like all models the idea of volume to get a notion of size. And one more thing I should say is this kappa here is a quantity that that controls that depends on the number of data, and it also controls something that's quite important for the effective dimension. So what is that? Well, if we think about these two spaces, the parameter space and the model space, right? So remember here, square root of the determinant of the Fisher gives us an idea of volume. All the effective dimension is doing is it's saying, okay, the Fisher information is important. It's a D by D matrix, right? So for one parameter set, we get one Fisher information. This is a D by D matrix where D is the number of parameters in your model. The effective dimension is simply counting the number of eigenvalues that are larger than a certain threshold. So we've got a determinant here. The effective dimension is trying to count how many eigenvalues of this Fisher matrix on average are greater than a threshold. And what is that threshold? That threshold is determined by this kappa here, which depends on the number of data we have. So depending on the number of data we have, we can see more eigenvalues that are contributing to the effective dimension. And what this means in terms of intuitive interpretation is the number of eigenvalues that are past this threshold that are considered important is telling us how many parameters are active and useful in our model. So all the effective dimension is it's counting on average for all kinds of parameterizations, how many eigenvalues of the Fisher information for every parameterization, how many of those are important on average. That tells us how many parameters in our model are important on average, right? And on average, meaning over the full space. But this is exactly the difference that I wanted to highlight, is that we talk about this effective dimension over the full model space, over this full thing here. And so this is what led us to call this idea of the effective dimension a global effective dimension. Now, remember, what we should be interested in through restrictions that we impose, like the learning algorithm, is a restricted model space, right? Because in reality, through things like gradient descent and finite data and so on, we actually don't have access to this full thing. We have access to a restricted part in this model space where we initialize our parameters and we train around there to find some optima, some minima. So what we did now, and this is the purpose of this new work, this continued work, is we redefined the idea of the effective dimension to be local, and this is the idea of the local effective dimension. So the formula looks quite similar, but what's changed here is subtle but really important. Is that we don't integrate now over the full parameter space. Instead, we integrate around an epsilon ball. So we average around an epsilon ball of this around this theta star, where theta star is a parameter set that we assume is an optimal parameter set after training. So we initialize, let's say, somewhere here in the middle. We initialize with some theta, and we train till we get theta star. And so then the effective dimension kind of understands, once we're at this theta star, how does the effective dimension look in this restricted space around this theta star, and an epsilon ball around this theta star that exists. So this is the idea of the local effective dimension. So in doing this, in redefining it this way, well, we tick this box of incorporating the learning algorithm, because now the parameters that we train to inherently incorporate stochastic gradient descent or whatever optimizer that we choose. And the next thing is like, okay, well, is this local effective dimension scale invariant? Because remember, multiplying your parameters shouldn't affect the effective dimension if you multiply by some constant. And thanks to the Fisher information, the effective dimension is scale invariant, because the Fisher information is scale invariant. It has this nice property of scale invariance inherently in it. So this box is ticked as well. And the incorporation of finite data is also imposed in the effective dimension, because remember I said that the number of data available to us controls this scale parameter that tells us how many eigenvalues in the Fisher information are important. So the fact that the effective dimension, the local effective dimension, is actually designed to handle finite data. It's very good for that. And then lastly, or not lastly, second to last, is, does it bound generalization error? Can we show this? And this was, I think, basically most of the focus of the paper was to prove this generalization error bound, which we managed to do. So basically on the left, we have this idea of excess risk of generalization error. And we were able to show that it can indeed be bounded. So all these crazy constants and weird things that you're seeing in here, the details, you can find them in the paper. But in short, the argument is quite straightforward and quite similar to the global effective dimension, is that you can bound this space, or you can bound this quantity rather by, there is a relationship that exists already with something called the covering number. So you can try to cover the space, and then you can relate the covering number to the effective dimension, and in particular to the local effective dimension. So there were just like a little bit of tricks and tweaks that we needed to do in order to show that that this is possible. So that's good. And now the last thing is to show that this local effective dimension can capture this over and underfitting behavior, right? So remember I mentioned that there are different experimental setups that one can embark on to try and show, okay, to try and actually force your network to overfit and see, does my capacity measure actually reflect this? So these are some experiments that we did, and what you're seeing in the red curve is generalization error. And on the x-axis in this picture here, you've got the size of the model, the number of parameters. So as we move to the right of this x-axis, we're making the model bigger and bigger, so larger and larger. Neural network, a classical model. And so as you make a classical neural network larger and larger, and you train it on MNIST, you would expect it to do better, right? So it's kind of, the generalization error goes down. And then you can see we calculate the local effective dimension, and it moves in a similar trend to the generalization error. So that's good, and something we would expect, right? So the effective dimension kind of goes down, and this makes sense because the effective dimension, remember, the local effective dimension is capturing the redundancy that exists in your model. Now, if you're making your model larger and larger, not all those parameters are going to be active, right? So if you look at the percentage of the active parameters in your model, as you make it larger, it makes sense that that percentage starts to decline. And then you can make an experiment, which has become quite popular now in classical machine learning, where you can force your model to overfit by messing with the data, by messing with the training data, and then checking how the generalization error looks on test data, on true data. So what I mean by messing with it, well, you can like randomize labels and shuffle them, and then train a model and force it to fit that shuffled data set, right? So on the x-axis here in this picture is the percentage of how much you randomize your labels for a supervised training task. And as soon as you go to like 100% randomization, I mean, this is totally noisy data that isn't sensical at all. So you would expect that your generalization error starts to go up, right? Because you're training your model on more and more nonsense. You're training your model on more stuff that doesn't make sense. So the red curve is increasing because you're increasing randomization and noise and entropy, whatever you want to call it. And when you check the performance of your model that's trained on nonsensical data, when you check it on real data, on the test sample, you will inherently start to do worse and worse, right? Because your model is not really learning anything, it's learning noise. And so similarly, we see that the effective dimension, after calculating this quantity on like a forced network to fit this random labels data set, it also increases, meaning that we are forced to use more and more parameters to fit this noise, which is quite interesting. And then we just kind of repeated exactly these two experiments for CIFAR 10, where in the case that your number of parameters for your model is a lot more than the number of data you have available to you. So we take the model sizes to quite a large amount here, and we still see the same trend. So in particular, I think we take it up to like 1 billion parameters, or I actually can't remember. So yes, so that's nice that we see that the effective dimension, the local effective dimension, does capture this under and overfitting behavior. Okay, so hopefully I've managed to convince you that these properties that I believe make a good capacity measure are satisfied by this idea of a local effective dimension. And maybe then, because you believe this, then maybe I also managed to convince you that the local effective dimension is useful. But now, what does this mean for quantum models, right? Because yes, it's all nice to understand capacity. We could go into that for a long time. But now coming back to quantum models, what we've seen with some preliminary numerics is that for some reason, the quantum circuits that we study can be designed to have a very, very high local effective dimension. Now, high local effective dimension for a model, what does that mean? Well, it means lots of the parameters are very, very active, right? They're being used. And now this might be a good thing, but it might also turn around to be a bad thing where the model is overfitting and it's not actually learning true relationships. And so the next thing is, well, like, how do we build and construct circuits, quantum circuits, to control capacity, to control this local effective dimension, such that we have a good balance between this bias variance trade-off, this under and overfitting regime. And will overparameterized circuits, right, quantum circuits, even behave similarly to overparameterized neural networks, right? Because overparameterized neural networks, or very, very deep neural networks, exhibit very interesting and strange behavior. Like, for example, so I'll point you to this paper here. For example, things start to become tractable when you overparameterize, and things become easy again. Like the optimization problem starts to become tractable. There is also like what we believe happening in deep nets, like implicit regularization that happens through training. And so this is also interesting, like where we see this kind of behavior. And lastly, this notion of overfitting actually doesn't become harmful in certain situations where we have these deep nets. We say that this overfitting is benign, meaning it's not harmful, but nor is it helpful. And so, like, will overparameterized quantum circuits exhibit the same behavior? And there is a very close relationship between all of these quantities that I'm talking about: generalization, capacity, overparameterization, and studying this interplay is, in my opinion, very, very interesting. And yes, if you're interested in that, then I encourage you to read more and and reach out to me. Okay, and with that, I am done. So thank you very much for listening to this talk, and I hope that I managed to get you thinking about capacity. And now let's try to, I think, understand it and see what does this mean and keep it in the back of our minds when we come to designing quantum circuits and quantum models. So thanks a lot.
Thank you, Amira. That was such a clear talk. I felt like I could follow every single one of your arguments. So congratulations on that. You just mentioned that maybe let's understand these capacity measures a bit more. Okay, so I'm going to ask you a question in lieu of that. How can we understand them? They are reminiscent to me to efforts that the quantum information community has done on quantifying entanglement, actually. That's where my mind went looking at this, right? So I want to ask you some questions that remind me of that. First, can you comment on how easy it is to actually compute these measures? I have some problem that I'm tackling. I have a certain approach, some certain data. How do I go and actually get a number for this local effective dimension? Is that tractable? Is that efficient?
Yes, so thankfully that is, I would say it is tractable, and we managed to do some numerics for models that are quite large. And the problem that one would run into is really just this estimation of the Fisher information. So in the case of this measure, like we used an approximation for the Fisher information called the KFAC approximation, which is quite interesting in its own right. And this allowed us to like exploit very nice properties of this approximation of the Fisher information. So we could decompose it into smaller block matrices and calculate the eigenvalues that's needed for the effective dimension. So it is definitely tractable for models up to a certain size, but one could, if we wanted to estimate the Fisher information more accurately, one could run into memory problems. But that being said, I mean, our numerics, I think, were pretty good. And the code, by the way, is available on GitHub through the paper. So anyone can go and check it out and just calculate it themselves. We also plan on introducing soon a calculation for the effective dimension for quantum circuits as well. So one could also start to play around with that on Qiskit. So to answer your question, it is it is calculable, it is tractable.
Okay.
But subject to some estimations.
Excellent, thank you. And then the other question is, how exactly should we use the information? So I have my model, I have my problem, I compute this measure of capacity, it gives me a number. How does that, can you tell us more about how in practice we can leverage that understanding to build better models, right? And to maybe have better performance. Yeah. How do we leverage this information?
Yeah, very good question. Yes, very good question. And actually it's not very clear, right? Because like I said, it might make sense at first to think, okay, well, I want to build a model where all my parameters are active and my effective dimension is very high, but this could easily lead to problems where, you're overfitting. And so this whole idea of capacity control, finding this balance, is something that is, it's very hard to do in classical machine learning. This is like, I think, the goal is to find this. So even though you can calculate the capacity, using the local effective dimension, what does it mean without comparison? And so I think it could be useful as a tool to compare certain models with different properties, but maybe the same number of parameters, for example. But controlling the idea, this notion of having a balance would also go hand in hand with understanding, okay, well, if my model outputs a local effective dimension of let's say 50%, whatever it is, it's saying half my models are active, half my models are inactive, then how does this model actually perform on test data? So what does the generalization error look like? And then maybe tweaking your model architecture to understand, okay, how do I make it less or more expressive in terms of the local effective dimension? How does that hurt or help my generalization error? Maybe probing it like in this sense would answer this question. But I think in full generality, it's very hard to say because it always depends on the type of data you have, the type of model you have. And a lot of these things are subjective and change.
Yeah, that makes sense to me for sure. Amira, maybe switching gears a little bit. I think you probably get asked this a lot, but I think it's a good thing to share anyway. I think one common theme of speakers at QHack is that most people don't follow a straight line in their careers, right? And I think your career path is particularly important. Do you mind sharing that with our audience? Especially that moment, if I recall correctly, where you were kind of working in finance and decided that was not your thing and did something very seemingly crazy to switch to quantum computing. Maybe can you tell us a little bit more about that?
Yeah, sure. It's a strange one because I grew up my whole life thinking that that I would go to university, and then like the whole point of going there and studying was just to get a degree, to get a good job, right? And then like, why do you want a good job? Well, you want a good salary, you want to be like, rich and have a nice house and so on. And so like, yeah, and so I chose a degree that I was told is would guarantee a reasonably good job, right? So this was something called actuarial science, and I knew always as a kid that I liked mathematics,
Yeah.
and I was told that this degree, has a lot of math, but it's also it would get you a good job in like a financial industry. So I did that, and it was interesting, and I went on to get a job at a bank, and then a finance company, an asset management company, and yeah, I just kept having this feeling that
Mm.
something was always missing. Like there was just something that wasn't satisfied, and so like I thought, okay, well, I'm like a curious person, so I always try to learn more, to do more. Then I got exposed to machine learning in my job, thankfully, because my team was pretty cool, and they were always looking at new tech and new ideas. But then when I found this idea of physics, and physics, by the way, I took in high school, but I never understood it. Like I think I still remember like my classes. I sat there like just blank. It was like a foreign language, and I never understood the relevance, right, of like understanding the trajectory of throwing a ball. Like that was
Yeah,
so
I hear you.
silly. But then when I found like um, the idea of quantum physics, and like even physics through the Schrodinger equation explained in a way that I understood. So I was watching a lecture about finance and modeling stocks on a stock exchange, and the lecturer related the Schrodinger equation to this Black-Scholes equation, which like models options and the prices of stocks. It was like something just switched on, and I was like, oh my goodness, like this is so cool, this is so interesting, and how far can this go? So I started like YouTubing more videos about physics, and teaching myself a little bit more. And the more I did this, the more I realized, okay, no, this is the thing that was missing. This is
Mm.
so clear to me. And even though I can like kind of picture where my career would go in finance, and it was on a good trajectory, I knew that I would be doing myself a disservice if I didn't actually change to the thing that I was truly interested in. So I remember I remember telling my parents, trying to convince
Mm.
them that I want to go back to university to study a master's in physics, and they were like, "What on earth are you gonna do with that? Like, what job are you gonna get? What?" And back then, it was a good question, because um, like all these positions in quantum computing didn't even exist. So so they were
Yeah.
right in like wondering that, right? I mean, they could have made the argument that I'd probably end up back at a bank. But I'm so grateful that I made that transition, and I followed what made me happy and satisfied my intellectual curiosity, because yeah, I've never looked back, and I've never ever had a feeling again like something was missing, because now it's just yeah, I've was fortunate enough to find it. So
I love that. You never had a feeling that something was missing again. That's a good reason to do something you're doing, I would say. For what it's worth, for me, studying physics was an act of rebellion, 100%. I didn't want to be an engineer. And then I just ended up continuing to like it. Amira, we have some questions from the audience. Thank you so much for sharing that story.
Sure.
Um, um, so again, these are more related to your talk now. E6 Peters is asking, so now regarding capacity scale invariance, so scale invariance, don't you think that this contradicts the idea that models can be regularized, so restricting capacity, by suppressing weights? For example, there's weight decay or loss penalty based on weight matrix norms in neural networks. So can you comment on that? Is scale invariance kind of contradicting the idea of regularization through scaling the weights and suppressing weights?
Yeah, so that's a good point. So I think maybe this like implicit regularization is something that also we conjecture, and to my knowledge, I don't think it's fully proven about how this works, right? So um, let's just think about linear models, right? So linear models, we know, converge when we use like learning algorithms like gradient descent. We know that they converge to minimum norm solutions. And so all I was trying to say, so I don't think there's like a contradiction here in understanding the capacity or the expressivity. All I was trying to say is like in terms of the function classes that a capacity measure can represent, whether you take the model of a certain architecture or type and multiply it or transform it by inconsequential transformations, this shouldn't change the expressivity. But that's like a really good point and a really good question, right? Because in terms of something else that I said about your parameters in parameter space kind of influence the restricted space that you have access to, which then we're trying to find the capacity of. Yeah, I mean, actually, this is something I never thought about, and it's really a good question, because then there is an interplay between this idea of scale and variance, because if you change your parameters, you're changing where you are in this restricted space. So I wonder, maybe, yeah, I don't know, maybe there is nothing, maybe there is no difference in capacity. And sorry, I'm just thinking out loud now and probably rambling to you, but it's
No.
it's an interesting question.
Yeah. By
Yeah,
the
I'm
way,
not sure.
that's probably Evan Peters, I think. So maybe you were just gonna talk to him about it
Oh
offline.
yeah, cool.
Amira, I hear we're getting some frames dropping in the stream.
Sorry.
I'm still gonna continue. At the very least, I want to hear the answers. Maybe this is not the case. So I'm just gonna shoot one more question, which I think is a really good one, and something I'm wondering about as well. So you talked about this notion of the restricted model space, right? And so the question from Antonio Jesus G is, how do we know what exactly is that restricted space that we can access?
Yes, very good question. And I think we don't really fully know or understand yet the behavior and the influence that we impose through certain restrictions, right? So I think this is largely still very exploratory, even in classical machine learning research, and for us probably not even heard of. So I think only maybe just 2 or 3 years ago, like we understand that gradient descent, for example, let's say we initialize somewhere in parameter space and we train with a certain learning algorithm like gradient descent, it actually doesn't take us too far away. Like the minima that we find with the trained parameters after our initialization, if we look at them at the trained parameter set versus our initialization, they're actually not that far away. And so understanding this restricted space means that we have to understand all these different things at play, right? We have to understand the learning algorithm that we use. What does it do? What does it transform in terms of our parameters? The model that we have. I mean, we still, in terms of neural networks, we still don't really fully understand what depth does to a model. We know that adding hidden layers is crucial for some reason for good generalization performance, for expressivity that's not harmful. But there's just so much that we cannot say. We can do numerics and we can say, okay, it just works. But we have to start somewhere. We have to start slowly. So yeah, I hear you with this question, but understanding this restricted space depends on a lot of variables, a lot of things. And just one more thing I want to say is that there's been some nice progress now in understanding it just for basic cases like linear models and linear regression. So if you're interested, watch the one of the lectures from Neurops, which I think is still publicly available. It's called the Posner Lecture, which was delivered by Peter Bartlett. They're doing some really, really great work, and in there he has a very nice literature review of this whole notion of restricted spaces and overparameterization.
Right. Fantastic. Amira, that's all the time we have left, unfortunately. I could keep talking with you, I think, for a very long time. That's how I feel, certainly. Thank you so much for joining us. It was a pleasure. Fantastic talk. And yeah, have a great rest of the day.
Thank you. You too. It's nice talking to you.